All right, so here I have the fourth week of NTI, finding the area between curves video. Um, this is going to be a bridge between the visual examples we had in week 2 and then last week's, which was using the fundamental theorem of calculus to evaluate definite integrals. This evaluation that we did, we didn't really see a lot of visual examples of it, but here we will, and you'll actually be writing a lot of these integrals. So it's important to note that the integral from a to b, those a and b, those are the bounds of integration. So when I reference them, we are going to be integrating from the starting a value to the ending b value, with a and b representing x values. And just to remind you what it is, we'll be integrating b and integrating the function, plugging in b and subtracting the integral of the function and putting in a. So that will come into play in this lesson. The first example, it's going to represent area, but the first example has a pretty simple setup. And I want to find the area bounded by the curves x squared, 0, 2, and y equals 0. Y equals 0 is a little redundant because the integral is already an integral already means the area bounded by the curve, the bounds, and the x-axis, which is y equals 0. So you can see I'm going to label everything, which you should definitely do if you get a chance. And it's not hard to make a little thumbnail of what you see as a graph, just to get a visual. And I did have to change this equation a little bit as it was shown in my text, just to correct it so it was the right one. So we actually have to write this integral, and I'm going to write from the left bound 0 to the right bound 2, and I'm going to integrate the curve, so x squared plus 1, and I'm going to multiply that by dx. So like I said, y equals 0 is a little trivial. And yes, we are finding the area bounded by curves, but just to re-emphasize this, you need to write the definite integral, because we're writing it and we're also interpreting the definite integral to be area. So if we carry on with this integration, we actually got 1/3 x cubed plus 1 plus x, and then I'm evaluating it from 2 to 0. So I'll plug in 2 first. So this is how last week was basically, and then I'll plug in 0. 0, this side is just going to be 0. But the left side, this left evaluated piece, is going to be 8/3 plus 2. So this is 6/3. So 6/3 plus 8/3 is 14/3. And I am writing units squared just to re-emphasize here that this is area. Now we have our next example. This is the area bounded by the blue and red curves. So we don't have equations given to us except for, or I shouldn't say we don't have the bounds of these equations given to us. We have to visually notice it. So what you'll see is an intersection here, and we'll come back and check that out. But remember, the area under the curve is like the integral is the area under the curve. So the area under the blue curve, I'm going to represent with these vertical slashes. There's the intersection, and then I'm going to have some pink slashes that go horizontally that are going to represent the area under this red curve. So we actually have, so if we were to integrate these things, this blue area and would be the integral of radical x, and the pink area would be the integral of x squared. So just to further emphasize this, I wanted to draw them separately from each other, just to show you what area they were creating. So there's radical x. And then the pink area looks like a little wedgy piece of doorstop, I guess. And if we were to, it looks like we could combine them to create the green area, which is what we need because we're finding the area bounded by the two curves. We wouldn't add them together. We would actually subtract them, because if I were to take the blue one and cut out the bottom of that piece, the bottom would represent the pink area. We would result in the green area. So essentially what we're doing is we're taking the function radical x and subtracting it, the integral of radical x, and we're subtracting it from the integral of x squared. And this will take a couple examples. And I'll do one more here, but you'll probably need another through quizzes or some sessions this week. So because all this happens from 0 to 1 over the x interval 0 to 1, I can write these two functions together in the same integral. I don't have to do two separate integrals. So this is all we're integrating. Not very complicated. You have to rewrite it once, but that's all there is to it. I rewrote it as x to the 1/2 minus x squared. I take the integral here, and I'm going to evaluate it from 0 to 1. I'm going to plug in 1. And then I'm not going to show plugging in 0 because this whole thing is just going to be 0. But it's not too hard to evaluate 1 here, so I'll just get 2/3 minus 1/3. So the area of this green space is 1/3. And I'm going to show unit squared just to show that it is an area in this case. It's not necessarily an area depending on the units we have, but we'll see. We'll talk more about how to use units with integrals in future videos. Again, draw yourself one of these pictures to help yourself out if you need to. So this is our last example. This is finding the area of the region R, and it's a little tricky because we're integrating with 3 functions, and it goes below the x-axis. And we've also got like a separation between spaces. So you can see that the left function, this cubic, is bound, like it makes an area between itself and the line, and then this triangular section makes an area between its line, like the sloped line, and then the horizontal line. So I'm actually going to draw these pieces separately just to get an idea of what the regions are like. So this is how you would answer these questions, is you would break it up into 2 separate areas, because this triangular region is not bound by the cubic function. So I represent it separately. So again, to carry on with the idea from before, we're taking the top function and we're subtracting it by the bottom function. So we'll actually take the x cubed function, the cubic, and we'll subtract -1, because that's this bottom function. And then to follow along with the same idea, we are taking the 2 minus x function and subtracting -1 from it. and integrating those two things. And here we will have to take separate integrals because x cubed minus -1, that all happens on the left side of our bounds. So we'll have to start at x equals -1. And I know this is x equals -1 because the coordinate. And I'll have to carry it to x equals 1. So I have one integral. And then the next one, I'll just add the two areas together. So I'll add the two integrals together. But the next one happens from 1 to 3. So from 1 to 3, I have this triangle. I have this triangle shape. And I'm subtracting a -1 because that's the bottom function. So these aren't too hard to integrate, but I'll carry through that and come up with an area. So here I've integrated x cubed, and I've integrated +1 to get those, and you can see that I'm going to be evaluating two different integrals separately but simultaneously. So this one, yes, it's a huge example. It won't be as cumbersome on you on the quizzes, but it's just showing you if you did need to separate these, how it would go. There will be one that is similar, but not nearly as difficult function-wise. The setup is really what we're looking at. So yes, we can integrate this, and after you get it set up, you can evaluate this with a calculator. I do it by hand here, just to show it can be done, and I end up with 2, I believe, or 4. Yeah, 4 units squared. So this was our final answer. I'd like you to try to do your best on the quizzes. Look at it. Maybe take some screenshots. I think it's helpful just so you can see the graphs, and then you can come on to Google Meet and we can talk about it. Thanks for watching the video, and I'll talk to you guys later.